Good day, everyone. This is the Salt Vine robot. Our team members include Juan, Mohammed, and myself, Abdul Malik, who are all majoring in electrical engineering. And we have Kevin as well, who's majoring in computer engineering. Our project includes building a soft vine robot that can navigate through tight spaces. We plan on using pneumatics to control how the robot moves. We will also be having both manual and autonomous mode. The reason behind this project included being able to make a device that can navigate through hard to reach places. And this can have numerous applications, such as in the medical field, being able to retrieve small objects within someone's body system, being able to retrieve certain active artifacts during excavation sites in archaeology, and also being able to help victims of natural disasters such as earthquake and provide instant relief. Our project constraints are mostly economic and environmental, time and educational, and safety. With economic and environmental, it is hard for us to provide all the funds for this project, being college students. And also with the pandemic, it has also created a constraint on logistical issues. And then with time and educational, it's hard for us to devote as much time as we would initially thought, because we have other responsibilities as well with classes and jobs and internships. And then educational being the fact that we're still naive in how deep this field is, and we're constantly trying to learn as we go on. And then safety-wise, with soldering components, that could be a huge safety risk because we're dealing with high temperature. And also with the pneumatics, we're also dealing with high pressures. And we could also risk other parts exploding depending on how we choose to manage the pressure. Our goals and objectives, just to reiterate, is to design a robot that can navigate through tight spaces. We'll be using both manual and autonomous mode to help the robot navigate through the maze or the obstacle course. And for our stretch goals, we'll be using a gripper system that can easily retrieve objects at the end of the course. And also in the autonomous mode, we plan to use CV or computer vision to program the way the robot moves through the obstacle course. Our project specifications are lined up as you see. We have our robot body, which would be of length 10 feet and 5-inch in diameter. Our lead acid battery will have ratings of 12 volts and 5 Ah. And our camera lens will have a focal length of 2.1 millimeters, FOV of 155 degrees. And our gripper radius should have 4 inches, body growth rate of 2 inches per second, and air pressure flow shall have 5 pounds per square inch and 10 cubic feet per minute.
For our project, we have decided to split the major task amongst ourselves. Juan will be mainly in charge of the electromechanical design of the project, while Mohammed will be primarily in charge in the PCB design and testing. I, Abdul, would also play a secondary role in this. And as for power design and testing, I primarily will be in charge of ensuring all the power design is accurate to the best of its abilities, and Juan will also provide additional help when necessary. And as for the software design, which includes the GUI, Kevin will be mainly in charge of getting it to work and run.
So here's the overall design of our robot. As you can see, we have a base, which would have the spool motor. And the spool motor would allow the body to grow and retract. The body also has a cap, which contains components such as the camera, the sensors, and the roller motors. The spool motor and cap connect back to the PCB. The PCB is what allows the motor to be powered up and controlled. And the sensor readings are also sent to the PCB, which is then sent to the PC via USB serial. The PCB also connects to the pneumatic harness, which allows us to control the various pneumatics and ball valves on the harness. So we can switch the valves on and off to control the robot movement. The pneumatic harness is also connected to an air compressor. This is what is used to inflate and deflate the robot. And the entire system would be powered up by a 12-volt battery.
So this is our block diagram. Starting from the top left in yellow is our power subsystem. Then in red is our camera and video processing subsystem. Then in gray is our motors. In blue is our pneumatic subsystem. In white is our custom PCB control board. In orange is our robot controller. And in green are our sensors, not including the camera. Moving on to the mechanical design, the robot body is the part of the robot that is going to be lengthening and retracting. Then the artificial muscles or SPAMs are going to be lining the diameter of the robot body and are actually going to steer the robot in any direction that we want in 2D space. The robot base is what houses the undeployed part of the robot, and it also serves as a pressure chamber for the robot body. The internal rollers are at the tip of the robot body, and they aid the robot in retracting onto itself. The tip-mounted cap is actually part of the same assembly as the internal roller and serves as a solid surface for us to mount our sensors and effectors. And the pneumatic controls are the part of the robot that controls all the pneumatic actuators. The body is made out of LDPE polytubing. This is very thin plastic that has a low bursting pressure of 3.2 psi. Over on the right, you see an image, an illustration of how eversion works. Basically, when we pressurize the robot body, it will lengthen it. It will lengthen by inverting itself. The pressure that we need in order for the robot to lengthen is about 1 psi, which is good because our max bursting psi is about 3. When we were picking the material for the robot body, we needed something that was flexible but not stretchable, so that it would not change size from one deployment to the next when it's pressurized. We could have gone with LDPE polytubing or TPU coated nylon fabric, which is similar to the fabric that backpacks are made out of. The problem with the fabric is that it is about 4 times more expensive than the LDPE tubing, and it also doesn't come in tubular form, so we would have to sew it and heat seal it in order to create a tube, and that's why we went with LDPE polytubing. The artificial muscles or SPAMs which stands for Series Pneumatic Artificial Muscles. They are the part of the robot that actually steers the body. Whenever you pressurize a tube, it actually shortens in length by a small amount. And by putting rubber O-rings down this tube, you can actually accentuate just the characteristic and make it more pronounced, so that when you inflate it, it actually contracts by a lot more length. And by putting these in all the way around the robot, we can actually steer the robot in any direction we want. More about the base. The base is, if you can see this air inlet right here, that's actually what's going to pressurize the base. And inside the base is a spool and a motor. So when we want to lengthen the robot, we will pressurize this base and we will spin the spool so that we can give the robot more material for it to lengthen. Then when we want to retract, we spin the spool in the opposite direction and sync it with the internal rollers at the tip of the robot for it to retract. The cap is the most intricate part of this entire robot as far as mechanical design goes. It has to be attached to the robot, but it also has to be able to slide up and down the material. So in order to attach it, but not permanently, we use magnets and ball bearings. And inside this cap is actually the internal rollers, which you can see here. The internal rollers are coated with this high friction material that is used for us to be able to grab onto it and push the robot material back onto itself. Moving on to the pneumatic portion. There are several pneumatic components, starting with the portable air compressor, which holds all the potential energy for our pneumatics. Then we have pressure regulators to control what pressure we are at, followed by check valves, which make sure that the pressure is only going in one direction. And then we have solenoid valves, which can be switched from injecting air to releasing air from the robot body and air muscles. And then we have pressure transducers on those pneumatic actuators so that we can measure how much pressure is in each one.
So for the pneumatic design, we built a harness that has 4 ball valves, 4 solenoid valves, and 4 pressure sensors. we tested this harness with the PCB and it's working properly. So the air compressor is going to pump air into the harness, and then we'll use the PCB to turn the pneumatics and ball valves on and off. And that would allow us to steer the robot properly. And the pressure sensor values are going to be sent back to the PC via USB serial. So for the hardware, we have an 80 mega MCU that's being used to control the 3 motors along with the gripper motor, and we're also using that to control the pneumatics. And we're also going to be feeding the sensor data into the microcontroller, which is going to be sent to the Raspberry Pi. And the hardware also includes a joystick and a few buttons that would allow us to control the pneumatics and motors manually. So when picking our microcontroller, we were deciding between the ATmega 328, the 2560, and the Raspberry Pi. We decided to go with the 2560 as it gives us ample digital and analog inputs, and also has enough PWM outputs for the motors that we have. It also supports I2C, SPI, and UART. We're going to be using I2C and UART. So here's the schematic for our microcontroller using the ATmega 2560. We added an ICSC programming interface, which is going to allow us to program the MCU after it's been soldered on the PCB. We also added LEDs for power and serial communication. We also have a reset switch, bypass capacitors, headers for digital and analog pins. That's going to allow us to use any extra digital or analog pins in case we need some. And we also added a USB serial interface using the CH340G chip that allows us to interface with any other serial device. And we're going to be using this to send sensor data and any other data. We're going to be using this to send sensor data to the Raspberry Pi via micro USB. So for the motors, we'll be using a 12 volt square phase gear motor that's going to be placed at the base and will be used to drive the spool. So as the motor goes clockwise, it's going to have the spool go in one direction, and when it goes counterclockwise, it'll go the other direction as seen in this diagram over here. And we'll also be using 2 metal gear motors for the roller motors as seen over here. Those will be placed at the tip of the worm and will help with retraction and growth. We also have an SG90 servo motor that's going to be used as the gripper of the robot, so that will assist with gripping items. And to drive the 2 gear motors and the square face gear motor, we'll be using an L293 motor driver, along with motor encoders for all the motors. So this showcases the motor schematic. We're using 2 L293 motor drivers, and so this showcases the motor schematic with the L293 drivers. We're using 3 PWM inputs here because we have 3 motors that need to be driven, and they all go to, and the output of all these motor drivers go to this header over here, and this will connect to the 3 motors. We also have decided to use interrupt pins 10 and 19 to be used to interface with the encoders. So we'll be using these pins to read the encoder value of the motors. So here's an overall block diagram of all of our motors. So we have the MCU here, and that's going to be used to send the PWM inputs to the motor drivers. And as you can see over here, we're using 3 motors, so we have 3 motor outputs. So one motor driver will be used to control the 2 roller motors, and the other will be used to control the base motor. And for the SG90 servo, we're going to have that connected to a digital pin along with the 5-volt and ground straight to the MCU. We'll also be incorporating a motor control switch that's going to let us switch the position of the spool motor. And so for our altitude sensor, we'll be going with the MPL3115A2, and it's going to be sending data to the ATmega 2560 over I2C. And this is going to let us send temperature data along with altitude and pressure data to the Raspberry Pi. So the MCU is going to be writing serial data to the Raspberry Pi, which is going to include the sensor values, and that will be displayed on the user interface as seen over here. And the sensor is going to be placed on the worm cap, so all the readings will be coming from the tip of the worm. So as it expands and navigates, it'll be sending back all that data from the tip. And to be able to use that sensor, we had to design a logic level conversion circuit, as the altitude sensor is a 3.3 volt device and the ATmega 2560 is a 5 volt device. So we used the BSS138 N channel transistor, which allows us to convert that 3 volt 3 signal coming from the sensor to a 5 volt signal. So on our PCB we have a header with the 3 volt 3 power and ground and the SCL and SDA, and that would be used to connect to the sensor.
For our main power source, we'll be using a battery, and we researched different types of batteries that will be appropriate for this project. And we ended up with two main batteries, the precision lead acid battery and the LiPo battery. After a detailed comparison, we decided to go with the lead acid battery because it's much cheaper, provides a higher amp hour rating, and the chargers are also very cheap and cost effective as well. Here's a simplified version of our power design. We plan to use our battery charger of 12 volts 4 amp to charge our battery, which would be 12 volts and 5 AH rating. We also plan to use two buck converters, which would reduce or step down the voltage to power a Raspberry Pi and altitude sensor. And here's the more intricate design of our power conversion. As you can see, we designed using Autodesk Eagle. We plan to use our 12 volt battery to power motors and pneumatics, our 5 volts, which will be stepped down using a power converter to power the MCU, and our 3.3 volts, which will also be stepped down as well to power the altitude sensor. Different functions as well, depending on how much heavy the electrical load can be.
So this is the overall PCB schematic. It includes all the schematics that were discussed previously. And this is our PCB board layout, which was designed in Altium. The left side is the top layer and the right side is the bottom layer. We utilized polygon pores to make the power and ground more spaced out and more efficient. Here's a 3D CAD model view of the PCB. There's a power jack. We also have a micro USB connection here. We also have various power sources that are going to be used to power our devices. So we have a 3 volt 3 power source, 12 volts, ground, and 5 volts here.
Will facilitate the communication between project components. It also allows the user interaction and for the user to get some feedback from the sensors. It also handles the computer vision aspect of the autonomous navigation in this project. Here on the right, we can see the overall diagram of how the user Raspberry Pi PCB and hardware components will interact all with each other. For the user interface, we're going to implement a user PyQt, the Python framework. It presents the user with some live feedback from all the sensors as well, so some feedback from the camera so the user can navigate space. As well, it allows mode switching between manual and autonomous mode. Here on the right, we can see our first sketch of what the user interface should be looking like by the end of the project.
The robot will have a manual mode and an autonomous mode. For the manual mode, the software GUI is going to write bytes to the PCB that are going to have it either go left or right, or grow or deflate. And we'll be using WASD and some other keyboard inputs to control the robot manually. And the sensors are also going to be sending feedback to the PCB, which is then going to write that same sensor data to the PCB over USB serial. And that data is going to be parsed in the Python software and be displayed for the user to see. For the autonomous mode, the PC is going to handle all the image processing, and depending on the object, depending on the location of the object, the algorithm is going to send signals to the PCB to follow the direction of the object.
For the sensor signal transmission, the sensor data will be received and transmitted among the PCBs via I2C. Transmission data will be transferred among all PCBs all the way to the UI. Controller signals will be received by the main PCB and used for motor and pneumatic control. And here on the right, we can see how the transmission and the controller class will interact with each other, as well with the sensors and the PCB.
So for the software integration, we're developing a GUI that's going to allow us to basically control the robot. We use libraries such as OpenCV, PyQt6, and PySerial. We also use Qt Designer to develop the GUI. We also developed C++ code for the Atmel 2560, which basically controls the various digital pins and analog pins on the MCU. We also use Visual Studio Code to debug the code. So for the GUI, we have the camera display, the camera feedback over here, and we also have sensor feedback, so we can display values such as the temperature reading, the acceleration, and the various pressure values. We can also set the mode over here with the mode selector to autonomous or manual, and we can also detect objects with object detection. We can also select the port of the USB serial, which is going to allow us to connect to the PCB and control the robot. Here is the debug window, which is what we're currently using to control the robot and the various components on the pneumatic harness. So we can basically control the pneumatics. We can turn them on and off with these radio buttons. We can control the ball valves. We can open them, close them, and pause the ball valves to control the pressure flow. And we can also control the motors. So we can have the motors go forward, reverse, turn them off, and control the speed. Here is a prototype testing setup. This is what we set up to test various components with the PCB and test to see if we can inflate the tubing and have it steer.
So with the help of the test setup that we made, we were able to successfully grow the robot using the software GUI. So by pressing the W button, we were able to start the motor running and open up the ball valve to inflate the robot. So we were able to have it grow, and we can also stop the robot with the keyboard input, which closes the ball valve. And to steer the robot, we used the keyboard input to open and close the specific ball valves for the tubes. We also tested the cap of the worm by inflating the body and then steering the worm in different directions, and then looking at the feedback through the camera and the sensors. So for the budget of the robot, we totaled at $1,795.62, which included the cost for all the mechanical components and electrical components. So in this project, we succeeded in developing a fully airtight base and body that could be inflated and deflated. We also succeeded in completely manually controlling the robot in all directions. We also succeeded in having a PCB that can read all the sensor data through the analog inputs and also control the motors and ball valves. We also developed Python software that can interface with the PCB via USB serial and write and read data. We also succeeded in developing a pneumatic harness that can inflate and deflate the body and its tubes. And for the difficulties, due to the time constraint, we weren't able to integrate the roller motors, which are used for retraction, and we weren't able to make the robot fully autonomous.